You may wonder why this looks like good news. Stay tuned, another update on the MicroPET. As you can see, nothing really has happened on the hardware side of bits. So what I've been working on is improving the code in the CPLD, making the signals more reliable and better in the timing. And then I've been working on the bootloader actually, and the character graphics generation on the video screen. So this is the result of a small test program. Sets up the character ROM data in memory for the video output, sets up the screen memory with a series of characters, and then moving those characters around continuously. This is the same test, but here I've been using the character set from the Commodore PET, which has more fine-grained lines than the ones from the Commodore 64 that I have been using in the previous test. It should even be possible to look at and read the text on an 80-column display, even with my, let's say it not so optimal composite video output. So let's have a look at the memory map of the system. The physical memory map is rather simple. There is a 512K RAM chip and there is a 512K ROM chip, which can make up bank 0 until bank 7, including for the RAM, and bank 8 to bank 15 for the ROM. In addition, there is the I/O area, which I've put in here separately, which is a window of 256 bytes at E8, page E8 in bank 0, like it is for the Commodore PET. So, and then there's one thing, unfortunately, with the 816, it boots in emulation mode and it boots in bank 0, which is unfortunate because there usually is not the actual code that should be running in bank 0. It would have been nicer if it would boot from bank 256 or the uppermost bank. Systems where you put in that chip that are not bank aware and are using emulation mode, they would ignore the bank byte anyway, so it wouldn't matter. But anyway, that's how it is. So what we have to do is we have to provide some initial memory mapping. In that case, we map the uppermost 16 kilobyte of the ROM chip into the uppermost 16 kilobyte of bank 0 for reading. So the bootloader code is put here into the topmost area of the ROM chip and then is mapped into the topmost code of bank 0 where the CPU boots from. Once the memory setup is done and the bootloader code has actually taken care of, for example, copying some, in my case, Commodore PET ROM content into the RAM that is here in the lower part in bank 0. The init mode is left, and then we get to the normal mapping of the address space. And what we have here is we have the typical Commodore PET memory map. We have 32K of RAM. Then we have the video, which is 2K for an 80-column display. We have some RAM as well. Then we have the I/O window at E8, page E8, and then the rest of the ROM. What is not shown here in this diagram is the video code only takes the character data, but not the actual pixel data for each character. And what is usually stored in the so-called character ROM chip in the Commodore PET or the Commodore 64. And this is taken from bank 7, actually from the beginning of bank 7, which is it's an 8K character ROM, which has 16 bytes per character, so you can have very, very long, very high characters with more than 8 pixel rows. And it also has 2 different character sets which are switchable by an I/O pin from the I/O chips of the Commodore PET. What is also implemented or going to be implemented is the memory mapping of the Commodore 8296 machine, and this machine has the capability to map the upper 32K in bank 0 in 2 blocks of 16K each, and each of the 16K blocks can be mapped to one of 2 separate RAM blocks in the original machine, and here I've chosen to use bank 1 for the different RAM mappings. So why is this screen a success? So this screen actually means that the computer boots into the PET ROM. So that means the bootloader is working, and it's copying over the ROM content from ROM into RAM, and it's also switching off the init memory mapping and jumps into the PET ROM code. And this is now waiting for some I/O, which is not yet soldered onto the board. So of course this is what was to be expected. What it also shows is that I've messed up my video output, because it obviously I'm only displaying 39 characters per character row, so that the last character, which is the space in this case, of the previous row is added in front of the next row, and therefore you get this kind of ladder. So some more work to do. So the next steps will be finally some more soldering, work on the hardware, and also fixing that video output bug. Thanks for watching, and see you next time.